Um, can you hear me? Or not quite? Um, okay, so this is our round table. Um, uh, the the motivating questions for this session is not the deep question over there about Brexit, uh, but it is connected to that in the following way. So let me put up this slide. These slides are by Roger Wetz. These two slides, the first three slides are by Roger Wetz. And actually it was ISMP in Amsterdam, I believe, not ISMP in Berlin. So the comment was, this is from a collection of papers on the history of mathematical programming that was compiled for that ISMP conference in Amsterdam. And as you can see, this is an assessment of stochastic programming by George Danzig, saying that it is interesting to note that the original problem that started my research is still outstanding, namely the problem of planning or scheduling dynamically over time, particularly planning dynamically under uncertainty. If such a problem could be successfully solved, it could eventually, through better planning, contribute to the well-being and stability of the world. And this is where Brexit comes in. So, so Roger put together some thoughtful questions for us to consider, and so I'm just going to go over it. So the first question is, could Brexit have been helped by solving a well-formulated dynamic stochastic program? Okay. As you can tell, this session is headed in a different direction than the previous one. All right, so the answer, of course, is yes. We all believe in stochastic programming, so yes. But then there are other issues, and so the challenges and formulation and solving of stochastic programming problems, I will not be able to do justice to this because the master is not here, okay? But I'll try to just read for you what was being suggested, which is that the stochastic programming involves dynamics, decisions, the description of uncertainty. There's a variety of issues that come into formulating stochastic programming problems. And some of these are in themselves major areas of study. And in stochastic programming, we're trying to grapple with all of them inside one setting, which makes it all the more difficult. And then, as a result, the complexity of stochastic programming problems are formally much harder than even standard optimization problems. And so what we consider doing often is designing an optimization problem which yields an approximating solution. And now question becomes, what do we mean by approximating this problem? And so what we need is access to a methodology that can efficiently evaluate the reliability of an approximating solution. This, to me, is a very realistic aspiration for our community. Okay. So this is a couple of slides from Roger Wetz, and what we will do is we will go through the sequence of presentations, and then at the end of it, John Burge is going to be the moderator asking us questions, and you, anyone in the audience, should also feel free to chime in to your views or your questions. And let's see if we can, I'll try to explain how this panel came about, so to speak. We were reviewing this comment by Danzig, and then we decided that perhaps we, being Roger and I, essentially were going through how is it that one can assess such comments today. And so there were different aspects of stochastic programming that we figured should have a say in this. And so we figured, you know, John Burge, having done all these difficult models, energy, environment, all kinds of stuff, so he could tell us about his views on the modeling aspects. And then we had the mathematics side to be covered by, in the continuous world, by our German friends from Werner and Rudiger, continuous and discrete. And then there was, I think, Dave Woodruff to do the software side, and then I'm to bring up the engineering side. So we'll see how it goes. John.
Okay. Wonderful. Yeah. Okay, so as Suvrajeet said, I was tasked with talking about models, and that made me think about kind of where we are as a group and how have our models influenced kind of the world outside this room, and how has the world outside this room influenced what it is that we've put into our models, and where are the differences, and maybe why have those differences arisen, and where might we be able to improve on things. Oh yeah, so the question was, how far has stochastic programming gone as a, no, you took that.
Oh, you want to just, I'll go.
No. Oh. How long has it gone, how far has it gone, and where might it go? So what are some of the good things? You know, I think our models are recognized. I mean, if you ask people, I think they know something about stochastic programming. I mean, people in other communities like computer science or maybe operations research or broadly. So I think it's seen as a framework that is useful, and you know, I think we have some right to be sort of self-congratulatory about that. We also see, you know, some practical uses that have happened in several areas. However, I think there are areas that kind of go back to the very beginning of the field 50 years ago, or 60 years ago. You know, so things like energy planning, we see a lot of talks that have been here about that, or I would say finance, but maybe asset liability management is probably more appropriate, that there are actually a lot of applications that have happened there. And to some extent in logistics, I think we've seen that, and that goes back to the very beginning of stochastic programming as well. So I think we've seen the models actually have impact in different areas. And in particular, you know, it sort of relates to Danzig's comments about planning. And these are all things that are sort of about planning, about trying to look ahead and maybe plan things out for a while. And I think that's had an impact. I mean, I think we see it when you go and maybe look at the literature in some other areas that are related to ours. You do see some people that set things up. In fact, sometimes even in operations management where I do some work, people set things up as stochastic programs. They recognize them as a stochastic program. It's not a particularly maybe practical way that they set it up, but they do use it as a paradigm. So I think the modeling environment has had an impact there. I think we've seen it. We do see some broader kinds of problems, some problems that have more of an operational character that actually relating to things that people do kind of day to day. And that's also quite encouraging. However, I think there's a number of things that where maybe we haven't had as much. I would say, you know, in comparison to some other modeling paradigms, things like Markov decision problems, you know, I don't think we have the kind of visibility and the recognition maybe that they have, or you know, Bayesian decision making. I don't think we're quite maybe at the level of Bayesian decision making, even though it's hard for me to tell what's actually different. And certainly, you know, nothing compared to what's happening in machine learning. You know, I don't think we see any departments that are sort of created around us. So, you know, compared to what maybe has happened, some of the successes of areas that you might think of as being quite related to ours, I'm not sure that we've made it there. And I see there are a lot of areas where maybe we should have had more influence. I teach a class in revenue management. I think of revenue management as being sort of a prototypical type of stochastic optimization problem, but hardly anyone in the world at large would see it that way. And so I think that's something that we're, you know, partly responsible for, and not getting our name into these things, or think about you know, recommendation systems, whether it's Amazon or Netflix. You know, those are the kinds of things that I think of sort of naturally as stochastic programming problems, but that haven't been cast that way, and that people have not looked at, and that maybe is an opportunity where we might have not picked up on. And despite the fact that there are many areas that do know about us, if you sort of branch out beyond the limited sort of mathematical sciences kind of areas, I don't think you see very much recognition, and that's kind of the, I think, something maybe where we could improve upon. So why, you know, what might be some of the reasons that we've ended up where we are? You know, I think we do really try to build models that sort of capture what's actually going on, and that have all this generality, and that you can throw everything into. We've sort of emphasized that as opposed to how can I come up with a solution today, or how can I come up with a solution in the next second so that I can make a recommendation to this person that's looking at their phone and has just opened up my app. Those kinds of questions, which you could think of as whenever somebody opens up that app, that's actually a stochastic optimization problem happening second by second. But you know, other people have kind of taken over that space, and I think it's partly our thinking about, well, we want to come up with something that really captures all the things that are going on there. Not necessarily that's the fastest, or just comes up with a solution that has to happen in order for that person to use that application. I think we've often had a focus on then, you know, trying to be general, but then on sort of focusing on structures that are convenient for us to do analytics on, and you know, convexity being obviously one of those. But emphasizing that to the expense of kind of fidelity with practice, I think, is something in terms of modeling where I think sometimes we fall short. It's great, you know, to have those structural properties, But when you put them in and it sort of destroys the validity of a solution, then that's not necessarily the best thing to do. And then this focus on planning, and Mario Pereira had alluded to it. You know, we have had this focus on sort of central planning because we like to sort of set up an objective and have a decision maker who's going to choose everything in that objective. But of course, that hardly ever happens in the world. You know, whether even in centrally planned economies. So that focus on sort of central planning over things that are competing and always changing, I think that's something maybe that has limited our applications as well. And I think we often do kind of, I mean, I think all fields sort of suffer from this. But we do suffer from the not invented here syndrome, that, you know, things that aren't sort of within our community, we sort of think of as not being things that are very useful for us. And I think that's something that we need to overcome in terms of putting it into our models, you know, taking some ideas from, for example, what they've done in machine learning, and, you know, maybe not emphasizing sort of the structural properties as much as just coming up with solutions. So what can we do to remedy these sort of things? Yeah, I think, you know, we don't have to be the most general in the world. I think we can sort of limit our models to kind of things like that recommendation system. Well, just come up with something, some sort of ad that people are likely to click on or not likely to click on, and maximize the probability that they click on it and you make money when they do it. You know, that kind of thing that might be very limited in terms of some kind of modeling framework, but that really might have a lot of value, and, you know, billions of dollars of value in that context. You know, relaxing some of these properties, obviously that's something that many of us have tried to do. And I think it's something that we have to consider, you know, going forward in terms of if we want to build models that people are actually going to be able to use. You know, we can't focus so much on those properties. And certainly, you know, one of the things I think that has held us back is not including learning, not including like the sort of learning aspects of gathering information, and that your decisions actually influence how you gather information. That's something I think that we've been guilty of not incorporating as much. You know, competition, from what I said before, that's something I think, you know, in terms of models, it's something that we definitely have to be aware of in order to make models that are actually useful for people. And just kind of a pet thing. And one thing that goes back to Danzig, I think that's one thing that Danzig would have mentioned. You know, he always thought of time as kind of a model parameter. We don't necessarily think of it as a parameter. We don't put it into sort of continuous context and then try to look at how time affects things. That's something that Danzig always thought of. He always thought of it in that context. He always saw things as time sort of marching along continuously, and that there's some influence of time on your decisions. We don't build models that actually put time into it. And I think that's something that we need to think about, to actually build models, again, that are useful for people. And, you know, to be open, not sort of focus on that not invented here, to be open to approaches that come from all kinds of disciplines and all different areas. And if we do that, I think then we'll make our models more useful. And maybe we'll recognize, the last thing is recognize that actual people are going to use these models. And so putting people in, I think, is another thing that we need to do to make our models actually get some traction. All right, thank you.
Okay, ladies and gentlemen, when I was asked to give such a presentation, I realized immediately that I had to substitute somehow Roger Wetz, and I didn't feel well. And I had an email exchange with him, but still I have to do it myself. And and of course, when you think about such a question, stochastic programs, or in that case, two-stage stochastic programs solvable, then you always do it in a specific time point with a specific actual knowledge. And my knowledge came from a recent paper that I have seen, or it was included into SPEPS, and I know that it will appear soon in web programming, by Hanna Susanto, Kuhn, and Wiesemann on complexity of stochastic programs. It is called a comment on an earlier paper by Dyer and Stauchi. And they discovered an error in that earlier paper, but re-established the result even a little stronger. And so we all know that stochastic programming problems are difficult. They are NP hard. And it's completely clear that the most important or difficulty in such problems is the connection of the integration with the kind of integrand which appears. And this is one of my starting points. Of course, those people who are doing Monte Carlo could now say, yeah, with Monte Carlo methods, under certain assumption, we can solve it, but possibly with very many scenarios, very large-scale models. And this is a point which is also of interest. And dimension plays a role, and this is one point which I would also like to address. But there is a recent strong development in numerical integration, which is mentioned here. It's a paper by Sloan and Wozniakowski from '98. It states more or less that numerical integration is strongly polynomial retractable for integrands belonging to Vetor tensor product mixed story of spaces. If, and that is their idea, was one of their main ideas, they introduced weights for the factors in the tensor product, and the norms, of course. And this gives hope. And in addition, it was not the only development. Another development was that the same people, namely Ian Sloan and this group, also found methods which showed that this complexity result also came to life by certain methods, namely randomized quasi-Monte Carlo methods, in that case particularly randomly shifted lattice rules. And of course our integrands do not belong to set spaces, but anyway, it gives hope, and I will come to this last point finally again. So this is how the proof in the paper by Hanna Susanto, Kuhn, and Wiesemann works. So you look at this very particular second stage problem. Yeah? It has a very simple structured objective optimal value function, and then they derived that the expected value function has a formula like this, and the most important part is that the volume of the knapsack polytope appears in this formula. And this shows that if we cannot solve this easily, then also the expected recourse is difficult. And this is exactly the idea of the proof, which is in that paper. The computation of this expected recourse function is NP hard, even within an absolute accuracy of a certain number, which depends on the dimension D and on the alpha, which appears on the model, right? Where is it? Here. Or on the right-hand side here. And when you look at that constant, then you immediately realize that it tends to zero exponentially with respect to the dimension D. So very often it is very small, which means this is not a very serious problem, because this epsilon is really very, very small in general. In many cases, say at least. Okay, but anyway, they re-established the original result which was had an error, as I said, and this was also extended in the second part of the paper to random recourse models, which are even more complicated, as we might expect. And this is the situation, and we have to live with that. And as I said, the reason is that we have an integrand which looks very nice in that particular case. In general, we all know that in case of, say, relatively complete recurse and dual feasibility, we have such a shape of the integrands, and they are, of course, more complicated than the one above, but they have a similar structure. And both of them do not belong to these tensor product Sobolev spaces that I mentioned earlier in the complexity result for integrals. So this is the situation, and how do we come out of that? But because I think the other result is not so well known, I would like to mention at least something about it. So one small chapter on complexity of numerical integration. So what they have a different language also for their complexity result. And what they look at is they look at worst case errors of the integral and their quadrature method here. So it's very general with general weights. And this worst case error is then considered, and they take the optimal one, the optimal error, where they take the infimum with respect to all such integration schemes. And what they define is they look at such number, which means they find the minimal sample size, so to say, such that the optimal error is smaller than or equal to epsilon, a given prescribed accuracy. Of course, the function space in which everything is in is of importance. I didn't talk about that, but we have a certain linear norm space of functions and a unit ball in that. And then they define polynomial tractability, strongly polynomial tractability, and they say that the method has a course of dimension. And polynomial tractability means that this minimal n has an upper bound with a constant independent on d on epsilon. And here we have exponential growth, but polynomial growth on the right-hand side. And strongly polynomial tractable means that the dimension disappears. So this is particularly nice. And this is the worst case, namely that it grows exponentially with the dimension. And now they were looking around for function spaces, and okay, everything can be also transferred to a randomized algorithm, so I will not talk too much on that. But a very unpleasant observation is that such Banach spaces of differentiable functions for any R is not among those for which we have nice result. It can even be shown that numerical integration on such basis suffers from the course of dimension. By the way, very surprising, only recently proved. And earlier it is known that such, as I said, tensor product mixed Sobolev spaces are defined here, have a better behavior. We have such a behavior of the error, which means we are close to having polynomial tractability, but not yet because of the terms, and we do not know how the constant looks like. It took some time, and it took the time until 98, when Sloan and Wozniakowski proved that numerical integration is strongly polynomial tractable on this space if the weights, and that was the idea, as I said at the beginning, the weights which weight the coordinates in that space, in the sequence of functions that we have, that they satisfy a condition like that. then the constants do not depend on dimension, and we have an estimate, as I showed you before, for strong polynomial tractability. Where is it? Here, right? Okay, that is the first part of the story. And now we come again to this randomized Quasi-Monte Carlo method, which was developed immediately after. And it shows that also the convergence rate of this method the right-hand side of the estimate does not depend on dimension. So there is big hope that also high-dimensional problems using such methods can be solved with a better convergence rate than Monte Carlo. And in that case, one has to satisfy a certain condition on the weights and the spaces. But anyway, such a choice, for example, is possible. The problem now remains, what about our integrants? They have kinks in the continuous case, and they do not belong to these spaces. One way out is looking at the so-called ANOVA decomposition of multivariate functions at a composition like that. And it is defined in a way that we require that the ANOVA terms satisfy such conditions here, that such a integral is 0. So we have a product density now. Only for those situations, this is well defined. And if we have such an ANOVA decomposition, then we know that the ANOVA terms are orthogonal in our L2 space with respect to the densities. And it allows to define the notion of effective dimension. And for those who attended my presentation here on the conference, I'm sorry that I say it again. And with these notions, one has a chance to explain why two-stage integrants are not so far away from functions belonging to such a tensor product Sobolev space, because ANOVA decomposition terms can be much smoother than the original function. Our original function had kinks. The function in the proof of this paper by Hanna Susanto, Kuhn and Wiesemann had only one, but in general they have several or many. And but the ANOVA terms can be smooth. Even the first ANOVA term, all ANOVA terms until a certain index can be smooth. And it depends very much on the effective dimension. And that is the way I am looking at this problem. When we just by chance are able to find out that the effective dimension of our problem is relatively small, then we don't have a problem, because we know that ANOVA terms are close to our function, and hence the functions are close to elements in the tensor product Sobolev spaces. And then we have everything strongly polynomial tractable, and the NP hardness is no further problem. But of course, in general, we have to live with that. That is the story that I wanted to tell you. Perhaps not all of you knew that so in this way. And in particular, using randomized Quasi-Monte Carlo methods might be of help to solve stochastic programs in the near future much better than before. Thank you very much.
Yeah, stochastic integer programs are solvable, but numerical computation rests on two pillars. There are only two things that we really can do when we come to numerical computation. That is, once we can solve systems of linear inequalities, and the second is we can calculate the greatest common divisor of two integers. So the first part is, let me be very rough here. The first part is convexity. When we have convex problems, analysis does the job, and finally, this is solving linear equations. When we do the non-convex part, then algebra makes the job for certain classes of non-convex optimization problems. So this might sound as very rough categorization, but my point here today will be that the potential offered by discrete mathematics for solving stochastic integer programs is widely underused. Many years ago, Roger Wetz told me, Rüdiger, you will show us finally how to get rid of the integers. And and the slides, that is the first slide that I saw, there was a sudden hidden belief that integers were gone. Then there was no integer reference on the whole slide, on Roger's slide. And I said, yes, I will try, but we will not get rid of them. We will have to handle them properly. And there are two major approaches to integer problem solving, integer optimization problem solving. The one is the dual approach. It's what is mixed integer rounding. So in Jim's tutorial, we got to learn many cutting plane things. And here I have copied 3 pictures from the book of Lawrence Woolsey on integer programming, showing the role of cutting planes in Gomory. In Gomory cuts, in mixed integer rounding cuts, and in disjunctive optimization, disjunctive cuts. So I will not address these cuts. Rather, I will address the primal approach here. And this is a very simple approach. Suppose we are given an optimization problem, and we have the following algorithm. We have a magic set B. A magic set B with improving vectors. We have a feasible point, and if there exists a B in B that improves our objective when going from xn plus 1 to xn, then we go. And if we don't find a member in B, then we know that we are optimal. That's the big magic that comes along with this set. And the question I'd like to elucidate a little bit is how to get these sets. And we will see, and sometimes I will go like in a computer game. Level 1, level 2, level 3. And level 1 will be the mixed integer deterministic optimization. Level 2 will be two-stage pure integer two-stage stochastic programs, and level 3 will be multi-stage. And the same basic patterns will occur in all 3 levels, and it's a matter of now filling this with algorithmics and with numerics. We will see that we always need a tailored ground set. So think of the integer points in Rn. Then we will need a tailored partial orders, and the existence. And we will see then that with these partial orders, an order is partial because not every 2 elements are comparable. Those who are not comparable are forming anti-chains. And we will see that there are no infinite anti-chains in these properly chosen ground sets. And indeed, then this set B is computable. It's computable by what they call a critical pair completion procedure, a completely different kind of algorithm compared to what we know from the cutting plane industry. So we have this. It finds critical pairs and completes. That means this solves the conflicts there. This will lead to an SP algorithm, stochastic programming algorithm, an augmentation algorithm. Augmentation algorithms are those like the boxed one over there. We move from feasible point to feasible point, and we will see that that here we can work scenario-wise, and we have a decomposition effect. So, and the bonus that we have is that the cardinality of the set B stabilizes. That means the set B in a certain interpretation does not become bigger when the number of scenarios goes behind a certain threshold. And this all has to do with work that is done by these people here: Gordon, Dixon, McLagan, Aschenbrenner, Hemmeke, and Nash-Williams. Here are the people, and the idea is in there. The idea that they all work, this whole work focuses on this idea. I have pictured the Z2, a positive orthant there, and we do not find in this set, taken any subset of lattice points, we do not find infinitely many in there that are incomparable. We do not find infinite anti-chains. So in integer programming, so we have the ground set is the getter points, the lattice points in Zn. The partial order is a orthant-wise order of taking the shorter vectors be the smaller one. This is with the two blue conditions there. We have sign compared sign. The signs are matching, and we take the shorter ones. And then there is this basic statement by Paul Gordon, Leonard Dixon, a sequence of vectors in Zn plus such that Pi is not comparable to Pj is called an anti-chain. And in Zn plus level, there are no anti-chains of infinite cardinality. Why is that helpful? So this is the picture again. Yeah? You do whatever subset you put in the dots, you will always be able to cover it with finitely many of these orthants pinned to points. There are different formulations. Every infinite set in Zn plus has only finitely many minimal points with respect to this partial order. Then Jack Graver entered the scene. He was the first to give to propose a set that fulfills these requirements. The set of all inclusion minimal points with respect to this order that I showed before. This leads to these Graver sets are special test sets, which are a field of active research in integer programming, and they have the same idea. You have such a minimization problem, and when you augment feasible points, that means you have directions B that you add to your you have directions that you add to feasible points, then you can see that they at least have to be in the kernel of the matrix A. The set given that way is a test set and can be computed via a finite algorithm. And the finite algorithm is a generalization of division with remainder. So division with remainder means while there is some g that is smaller, subtract. So 8 divided by 4. Yeah? 8 divided by 4. If you can subtract 4 from 8, then you do, and you do it exactly twice in this case. 9 divided by 4, you can do it twice, and 1 is the remainder. This simple principle, with respect to this partial order, yields this. This is in the heart of this completion algorithm that I show here. You form pairs, and you reduce. Reduce means doing division of certain objects, and that all this is finite. In the end, the reason for this being finite is that you have only finitely many anti-chains, finite anti-chains in a set of proper structure. You see that the proof for the termination is the following: as long as you reduce this normal form, you find smaller points. From F plus you get to G plus, and we had seen before that this cannot be infinitely many, because if we would be able to do this infinitely often, we would have an infinite anti-chain. So exploration. Now stochastic programming. If we apply this was level 1. Level 2, we have a 2-stage stochastic program, like this. The first we observe is that feasible vectors in the kernel of AN. Remember, the kernel was the if and only if already the short pieces are in the kernel. So what you do then is you can conclude by permuting the VI, you do not leave the kernel. You can take these non-minimal elements there. Let me see. What you do is now you go to other objects. You have the first stage vectors U and the second stage vectors V1 to Vn, and you put them in pairs. You instead of operating, that's level 2, instead of operating with integer vectors, we now operate with pairs and have to translate our general scheme, completion, division, minimal elements, to this pair language. And in the pair language, we have for instance, the reduction or the definition amounts to certain rules, and you see it's just a specification. How do now monomials enter? Monomials that these are polynomials, power products of polynomials, where you identify the exponents with first and second order, second stage elements, and you do the whole round again. Now the theorem is, if you have an infinite collection of monomial ideals in a set of polynomials, this has no, then there are two that are contained in each other, so has no infinite antichains. And this forms the basis for a proof that the procedure for two-stage stochastic programs, where we work scenario-wise, is feasible. The final step now, yeah, here I'll show you. Here you can see how, for the two-stage case, these patterns can be followed with a proper, the definition of the sum of two polynomials has to be modified, and the normal form algorithm. Some more graver sets for linear multi-stage stochastic integer programs are existing. The decomposition into finitely many building blocks independently on the number of scenarios still remains, and completion type algorithms for computing graver sets also remains. And this can be proven by using the theory of better quasi-orderings of Mr. Nash-Williams here. And this has been done in a paper by Aschenbrenner and Hemeke in Foundations of Computational. And here's the level 3 statement. In level 3, we consider collections of monomial ideals in a polynomial ring, and we consider an infinite sequence of collections, and then we are able to show that collections form antichains, no finite antichains, and this gives but level 1 already gave us the pattern on what to do, and in the way I presented it here, it shows the state of the art there. So it's basically it's laying there and waits for implementation and for exploitation. I'm aware that this is quite abstract stuff, and also which is quite different from how we think about the stochastic programming solution methods so far. But it is an interesting, it is a powerful tool, I think. The tool, it becomes powerful when it is possible to identify subclasses of integer programs where we can solve this. Because the major result that was a little bit under stressed here, the number, so with the number of scenarios going to infinity, we always have a certain point where our test set remains the same. So the set B from the very beginning in stochastic integer programming remains the same from a certain level on. Yeah, I'm aware that we have seen the complexity. There's bad complexity, but here we have I think an orthogonal approach in completely different patterns, and the algorithm that I showed there, by the way, is one where you can do both. You can solve linear equations. So Buchberger's algorithm is the algorithm where you can do both, solving linear equations and calculating the greatest common divisor of two integers. Thank you for your attention. I'm waiting for questions and discussion. Yeah. I know.
Thank you. Following Werner Römisch by two things. And in that first time was 23, you probably don't remember this, and Dave Morton was in the audience. It was about 23 years ago. There were only 7 in the room. Werner had beautiful slides. I mean, beautiful in the handwriting sense of beautiful, plus beautiful mathematics. And Danzig was tremendously impressed with both aspects of these things. I had computer-generated slides, and my job today is to talk about computation. Danzig quickly found a mistake in my slides, and that was kind of how I remember the thing so vividly. Anyway, I've been asked to talk about computation, and I wanted to make it clear that it's not my fault that you're listening to me. John Paul Watson was invited to talk about computation, but I will instead, and I'll keep it fairly short because in a way I don't have that much to add to what John said. I want to talk to those of you in the room, and there's quite a few of you who are getting excited right now. And I mean, this is good sports right here. This is really good. I know you're a little tense because the right-hand side's cut off, but it's gonna be okay. The pre-solve does a lot of work. This was written by our software that writes out an extensive form. This is for an SSL, a large SSLP instance. And if you're like me, this is way better than sports, right? This is my favorite sport, watching C-plex traces. This is a big problem. They come out at about the right pace. I'm sorry, if the last shot of the NBA Finals was in the air, but a trace line came out, my head goes to the trace line, right? Same thing, penalty kicks, last penalty kick, I look at the trace line. And this is pretty good. This is a large problem running on a large computer. And you can see there's a lot of action, right? I mean, it really gets after it and quickly gets, this is still at the root node running heuristics. Just to show the heuristics are still looking and they've bogged down, and so now it's time to start branching. But once again, you see that it's stuck now. It's made a tiny bit of progress. I'm sure you're dying to know what happens in the end of, some of you want to know, so I'll click it forward and show you that it took some time, but we get down to a MIP gap of about less than 1%. So that's what we get to. And you can, I'll send you the slides later if you want to really study what happened here. But and I have just a couple of slides, so I want to ask the question, did we solve it? And what did we solve? Well, no, we didn't solve it, right? I mean, we did not achieve a provable, one of the probably many provably optimal solutions. But on the other hand, yes, we solved it, right? And this kind of comes back to what John said, in that we solved it in the sense that we can hand you a solution and we can even tell you a bound on its quality. Now, the only thing we solved was a discrete extensive form, and if the underlying problem was from some continuous distribution, then we've done something that's very helpful to solving that, but we haven't really solved that problem either. I now want to duck the question. These other folks have done a really good job of answering it, and I'm going to ask a slightly different question, which is, this is closer to what John was saying, can we provide a solution, not necessarily a mathematically provable solution, but a vector that gives you some values and some analysis to go with it? And we can do that sometimes. I think an impediment on the software side is that as a community, operations research in general and stochastic programming in particular is not particularly software oriented, which impedes the flow of mathematics to computation. So John mentioned some communities, and computer science broadly and even statistics have some advantages that we don't have in terms of infrastructure. And so, and maybe there's nothing we can do about that. So in statistics, if you have a new estimator, you put it in R. And if you were to stand up here and say, I have a new estimator, and you didn't put it in R, people wouldn't take you seriously, right? I mean, that's just not part of the culture. And in computer science, same thing. I have a cool way to make recommendations. No one would even ask, do you have software? Because it would be absurd to make that statement if you weren't putting out software. So that's just the way our community is. And I also think that in terms of solving the original problem as presented by a practitioner, we have, not that there isn't room for continued improvement, but we have pretty good ways to solve extensive form problems and even to solve stochastic problems. Maybe what's lacking more than anything is analysis. In other words, can you tell the practitioner which scenarios or which parts of the distribution or which aspects of the problem cause the solutions to look the way they do? That's probably an area with even more opportunity. So I promised to be short, and I was. Awesome.
So what I'd like to do is to actually give a preview of a new thing that we're trying to do. I've never talked about this before, so this is the first time I'm talking about it. So you probably will see a few typos. But anyway, here's what we're trying to do. We're trying to create an experimental infrastructure, just what Dave talked about. We're trying to create an infrastructure which will help you recognize if the solutions you're getting are any good or not. And of course, you may not. We don't have the whole thing all worked out. But here's the overall design of things. So the overall design, Dave mentioned R. So the overall design looks something like this, which is you get some data, perhaps from R, perhaps your own thing that you've put it into R. You validate some of the data. So the user basically puts the data set to create scenarios or some version of your probability distribution. And then you also create a model. This is Dave Woodruff's creation, actually, this PySP. Dave and John Paul and others have created this Python-based setup. And then from here, after you do the validation, you create an SMPS file, which many of us have worked with over many, many years. And the reason for doing the SMPS file is that there are many solvers that use SMPS files. You can, in fact, put an LP solver. You can have an MPS file and an LP solver in there and see what the LP solver would do for your stochastic problem. And it's actually very engaging to see what happens when you take a stochastic problem and have it solved by just take the mean, plug it into the LP, have it do the solution, and then try to do this output analysis and data and output validation. It's very, for those of us who grew up with LPs, you start realizing how off you can be under uncertainty, actually, because the distribution looks awful. And anyway, this whole thing is built so that is being built. I am not there yet doing a demo or anything, but I'm just showing you that here's what we're trying to do. And the goal of this is to actually have the user create a data set from some data they may have. One of the disadvantages that we have compared with the computer scientists is that in machine learning, much of the data that they get is already in the machine readable form. For instance, if somebody is giving you a handwritten document, and those handwritten documents have been scanned in, and the scan has the machine readable parts that from there they can go ahead and interpret each letter. And so the input part is basically very automated. In our case, it's not that automated. We have to actually build all of this. So what we're trying to do is to help the user just focus on the data set and the PySP model. So if you can set up this algebraic model, this PySP model is an algebraic model. So if you can set up an algebraic model and if you can put into the data set that is a flat file, in that case, you can get an SMPS input files, you can put it into a solver, and so these parts here, this output analysis, input validation, these things should be supported by your infrastructure. So our goal here is, like I said earlier, I'm the engineer here today. And so I'm trying to create this environment that will help people get into trying to determine if they're satisfied with the solution. If they're satisfied, then we've solved the problem. If they're not satisfied, then we have to do something more. So what I'll do is I'll give you some 2 examples. I'm not going to really go through the formulations or anything. I'll just give you where we think things are going. So this is some advertising and production example. This advertising data set is from R. You go into R, there is something called the advertising data set, and the advertising data set tells you that if I advertise in TV or in radio, then here's the kind of sales that I will expect. Okay, it's a random quantity. And what they can do is do a regression and give you, here's the regression from that investment. And then there is a production planning problem. Some of you might have used Hillier and Lieberman. There is this small 2-variable problem, which is called the the window example. And you can just take that production planning problem together with that advertising problem. The advertising problem gives you the sales data prediction, and this production planning gives you your constraints, and you can set up your stochastic program using that infrastructure. And similarly, we have an inventory example. This one here is cross-sectional data. This one here is time series data. And again, this SP model provides you some recommendations. And now, so the question becomes, what did the data do? So if you take a look, here was the data, and you do in true machine learning, statistical learning style, you divide up the data set into its training part and the validation part, and you can see that there are certain parts. So the X is the training data, the Y is the validation data. So if you split your data set in half and half, the way they normally would try, and you might find that, look, this lower part is not fitting very well. And so you might realize that perhaps the regression that you did is not as good. Maybe or if you want to do a regression, excuse me, I'm a little thirsty. You may want to divide up the data set in a different way, for instance, right? There are ways that people can divide data sets, and you can do that analysis without a great deal of trouble, okay? But anyway, let's suppose that you wanted to run this, and you run it, which means you have to create your PySP model, which is an algebraic statement of the problem. I'm not going to go through the model itself. It's not necessary. You can run it, and it gives you an objective function estimate. It gives you a confidence interval. And that's now going to be up for validation. Well, you run the validation, and it turns out to be reasonably close. At least the objective function mean falls within the validation 95% confidence interval. You say, okay, maybe even though my data set didn't quite do well in the sense of the input, but the output from the problem seems to be okay, at least on a broad confidence interval level. At this point, you can draw your validation set from the objective function side, if you like. And notice one thing. This one is not as bad. If you look at the fit here, there are only a few points that are away from your... No, it's the 1 minus. It's the 1 minus. So MATLAB, for some reason, gives you this 1 minus thing. So, but if you look at it, if you look at this, it's tells you that the objective function estimates weren't as bad as the input data estimates. But if you don't accept it, you can go back and redo your data set again, if you like. I can do the same kind of thing with that inventory example. This, of course, has a slightly better data fit. But if you didn't want, if you ran it, again, the same set of things, you can once again get the objective function. And again, there, oops, excuse me. The objective function, again, is off. But again, you know in what points of the distribution, this is what Dave was mentioning, so to speak, that at certain parts of the distribution, you're having trouble. Certain parts, you're not having trouble. So you can see that at this part of the distribution, you're doing fine. It's this part of the distribution you're not. Okay? So what this does is at least give the user a sense of where things can go wrong. And that's the basic idea. So basically what we're trying to do is to get some modern statistical tools as inputs. We want to do the output analysis and get SP algorithms that you can't want to solve very large problems without have computing support. And so this is, and part of the things that we are hoping to be able to do with this output analysis is this back testing. All this, the stuff that I showed you is back testing. It's not the forecast, so to speak. It's just the data that you already have. So you do the back testing. You can do some stress testing, which is looking at the extreme values. You can interface with simulators, so you can do forward-looking analysis. And I won't go through all of this, but this is basically the hope of getting stochastic programming into some infrastructure-ish setting, so that our machine learners can get a little competition from us. That because they're right now not able to do these kinds of problems yet. They're very able to solve problems where the data is directly from machines, such as speech processing, image processing, those kinds of applications. But the business applications of this nature, they're not yet able to handle reasonably. But the stochastic programming community, if you guys had such a tool, I presume that you should be able to work in the algorithms and software into such an environment. And so, one last comment that I want to make. This is something that I wanted to, just a happenstance. I just figured I'll go back to 1991 and look at algorithms that were going on in 1991, just for the heck of it. And it turns out that here were the two-stage sampling algorithms and two multi-stage algorithms that happened in 1991. Where are they in 2016? They're still alive and kicking. So they're all doing well. All right, so anyway, my conclusion of all this is that it depends on the p-values and r-squareds and so on and so forth. So it depends. We don't know. Depending on your problem, we may or may not be able to give you solutions, but we should be able to have an infrastructure that helps you make that decision. That's it.